Have you ever wondered how physicists can predict the exact path of a rocket? Or, something as simple as the speed of a falling apple? Well, it all starts right here with the basics of one-dimensional motion. In this explainer, we're going to pull together all the key concepts from Chapter 3 of the University Physics textbook and give you the ultimate summary.
So here's our game plan. We'll kick things off with the big idea. What is kinematics? Then, we'll get fluent in the language of motion, all the key terms. After that, we're going to open up the physicist toolkit, those key equations. And finally, we'll tie it all together with a rapid-fire summary of the entire chapter. All right, let's get into it.
First up, what are we even talking about when we say motion? This first section really sets the stage for, well, everything that comes after.
I mean, just think about it. From the way galaxies swirl through space to the tiny dance of atoms, our entire universe is in constant motion. And to make sense of all that, we have to start with the simplest case, one dimension. So picture a high-speed maglev train on a perfectly straight track. That's exactly the kind of motion we're going to be dissecting in this chapter.
The key concept here is a big one, kinematics. What it really means is that we're focusing purely on describing motion. Where an object is, how fast it's going, and how that speed changes. We are not, I repeat, not asking why it's moving, yet. The forces behind it all, that's a whole other fascinating story for another time.
So, to describe motion accurately, we all need to be on the same page. We need a shared vocabulary. Think of these next few terms as the essential language for any physicist.
Okay, let's start with the absolute basics. We've got kinematics, which we just covered. Then there's position, displacement, distance, and time. Now pay super close attention to the difference between displacement. That's just your change in position from start to finish, and distance traveled, which is the total length of your path. They sound similar, but they're not. Go ahead and pause here if you need to let these definitions really sink in.
Now we get to a really crucial distinction in physics, speed versus velocity. Your car's speedometer, that tells you your instantaneous speed, but velocity includes your direction. So, are you going 60 miles an hour or are you going 60 miles an hour north? That little difference is what makes velocity a vector, and honestly, it's a key concept for solving pretty much any physics problem.
And our final set of terms covers acceleration, which is just the rate of change of velocity. We also have a few special cases that you're going to see in problems all the time, like free fall, where gravity is the only thing acting on an object, and two-body pursuit problems, where you're trying to track two moving objects at the same time.
Okay, now that we have the words down, let's look at the tools. These equations are how we take all those concepts and turn them into powerful predictive math.
These formulas, right here, are the absolute heart of problem-solving in kinematics. They're the mathematical link between displacement, velocity, acceleration, and time. Trust me, mastering these is the key to mastering this whole chapter.
And here they are. Now, I am not going to read all of these out loud, but you can see we have equations for everything from basic displacement and average velocity to the equations for constant acceleration and the special cases for free fall. Seriously, this is the perfect spot to hit pause, review these, and maybe even write them down. This is your toolkit for the entire chapter.
All right, so we have the vocabulary and we have the tools. Now, let's see how it all comes together. We're going to do a quick walkthrough of the chapter, section by section, to see how these concepts build on each other.
So Section 1 really lays the foundation. It officially defines kinematics, hammers home that difference between displacement and distance, and introduces average velocity as just displacement over time. It's simple, it's clear, and it's absolutely essential.
Next up, we zoom in from the average velocity to instantaneous velocity. So what's the speed right now, at this exact moment? This is where you get a little peek into the power of calculus, which tells us that instantaneous velocity is the derivative of the position function. But hey, even if you're not in calculus yet, you can see it on a graph. The slope of a position time graph at any single point gives you the instantaneous velocity at that exact moment. Pretty cool, right? Next, we bring in acceleration, which is simply the rate at which velocity changes. And just like with velocity, we can talk about the average acceleration over some amount of time, or the instantaneous acceleration at one specific moment. And yep, you guessed it, that's the derivative of the velocity function.
Now, this section is where things get really practical. For the very common case of constant acceleration, we get to use that whole toolkit of kinematic equations we saw earlier. The real skill here is learning how to look at a problem, identify what you know and what you need to find, and then picking the right tool for the job.
And free fall is a perfect real-world example of constant acceleration. If we ignore air resistance for a moment, any object falling near the Earth's surface accelerates downward at a constant rate. We call that g, and it's about 9.81 meters per second squared.
And finally, the chapter gives us another peek into the power of calculus. See, if taking derivatives lets us go from position to velocity to acceleration, then doing the reverse, using integrals, lets us go backwards. We can start with acceleration and work our way back to velocity and then all the way back to position. It's an incredibly powerful tool for more advanced problems.
And that's our high-level tour of one-dimensional motion. You now have the fundamental framework that physicists use to describe and predict the movement of, well, everything from a falling leaf to a soaring rocket.
So, I'll leave you with a final thought to take with you. Just look around you right now. Can you see kinematics in action? Is it the constant velocity of a car driving by? The free fall of a pen you accidentally knock off your desk? Take what you've learned here and see if you can start describing the world in the language of physics.